In this video, I'll talk about our work on shaping logs via large sieve inequality. We'll give log factor improvements for problems such as sparse convolution and others. Let's first look at the definition of the convolution problem. We are given two arrays A and B, and we want to output a third array where the kth element is defined as the sum of the product of AI and Bk minus I, where I ranges from 0 to k. In this work, we focus on the case where all the input entries are integers. This convolution problem is equivalent as the problem of computing the product of two polynomials. If we encode the entries of the arrays using the coefficients of the polynomial, then the product of the polynomial gives us the convolution of the two arrays. Because these two problems are equivalent, in this talk, we'll use the polynomial notation. It is well known that the convolution between two length n arrays or two degree n polynomials can be computed deterministically in order n log n time using the fast Fourier transform or FFT algorithm. Because we care about log factors in this work, we need to specify the computational model. Here, we always work in the word RAM model with order log n bit words, and we assume bit operations and standard arithmetic operations such as additions and multiplications between machine words can be done in constant time. And we also assume all the input entries are integers bounded by poly n so that they fit in constant many machine words. It is conjectured that this order n log n time for polynomial multiplication is optimal. Now let's look at the sparse convolution problem, which is the main topic in this work. In this problem, we are still computing the convolution or the product of two polynomials, but the difference is that here, the number of terms in the input polynomials could be much smaller than the degree. And we assume that the input polynomials and output polynomials are given in the sparse form, which is a list of all the non-zero terms. Let's use this zero norm notation to denote the number of non-zero terms in the polynomial. Then we use this small t letter to denote the sparsity parameter of the input instance, which is the maximum number of terms in the input polynomials and the output polynomial. In this example, number of terms in the product is only 5, but the degree is as large as 32. And the natural question is to compute sparse convolution where the running time is measured in terms of the sparsity parameter t instead of the degree bound n. This will be very helpful when t is much smaller than n. The brute force algorithm that enumerates all the pairs of coefficients runs in t² time. And the best time complexity in t that we can hope for is order t log t time, which would match the best known n log n time in the dense case. So the natural question is whether we can achieve this running time. Before talking about previous works on this problem, let me first mention that this sparse convolution problem has a lot of applications in fine-grained complexity and algorithm design. This has been used to solve some string problems such as block mass pattern matching and sparse pattern matching. And it has also been useful in solving several variants of the subset sum and knapsack problems. And recently, this also used to solve some special version of the three-sum problem, which is helpful for proving three-sum hardness for several graph problems. In most of these applications, they use sparse convolution to solve this particular problem of computing the sum set of two input integer sets A and B, where the sum set is defined as the set of integers that could be obtained as summing two integers from these two sets. And the desired running time should be proportional to the actual output size, which in some cases could be much smaller than the naive upper bound size of A times the size of B. Now let's look at some previous works on the sparse convolution problem. Recall that n is the degree bound and t is the sparsity bound, which could be smaller than n. For the purpose of this talk, we can think of n as being a large polynomial in t, such as t to the 100. This case is already very interesting. Let's first look at the special case, which is called sparse non-negative convolution, which means that every input coefficient is a non-negative integer. This is an important case because, for example, in the applications on the previous slide, the instances that are in the applications are actually non-negative instances. For this non-negative sparse convolution problem, previous work by Breeman, Fisher, and Knuckles gave a deterministic algorithm in near linear time in T, and the number of log factors in this running time is 5. And if we allow Las Vegas randomization, then there are algorithms with better log factors. In particular, Breeman, Fisher, and Knuckles gave a Las Vegas algorithm in order T log T log T time. And if we further assume Monte Carlo randomization, then we can actually achieve order T log T time by the work of Breeman, Fisher, and Knuckles with a small additive polylog n factor in the running time. This Monte Carlo algorithm has error probability 2 to the minus root log t. And there are two open questions mentioned by the previous work. First, can we get rid of the log t factor in a Las Vegas running time? And second, can we improve the Monte Carlo algorithm to work with a high success probability, which is 1 minus 1 over poly t? Now let's look at the sparse general convolution, where the input coefficients could be integers that are possibly negative. This case is much more difficult because there could be cancellation in the terms. So the sparsity of the output polynomial could be much smaller than what it would be if there were no negative coefficients. For this problem, there are also near linear time Monte Carlo algorithms from previous works. But all of these algorithms have at least 2 log factors in the running time. And an open question asked by the previous work is that whether we can achieve T log T time for sparse general convolution with possibly an additive term of polylog n. Now let's mention our new results. First, for sparse non-negative convolution, we give a new Las Vegas algorithm that terminates in order T log T time with high probability 1 minus 1 over poly T. So this is a simultaneous improvement of both of the previous Monte Carlo and Las Vegas algorithms. Second, for the sparse general convolution problem, we gave a Monte Carlo order T log T time with constant success probability, but it only works under the restriction that the degree bound n is at most T to the 1.99, which is truly subquadratic in T. So this result does not fully solve the open question, but it makes a first step. We can compare with the previous progress on the non-negative case by Breeman, Fisher, and Knuckles. They designed their non-negative sparse convolution algorithm in 2 steps. First, they solved the problem under the similar restriction that the degree n is at most poly t. And then they gave a length reduction procedure to reduce a large n case to the small n case. So in our sparse general convolution result, we complete the first step, but the second step is missing. And the hope is that if we could design such a reduction for general sparse convolution, then this would fully solve the open question of achieving order T log T time for sparse general convolution. Now let's mention our third result on a different problem, which is called text-to-pattern Hamming distances. The Hamming distance between 2 strings is defined as the number of differing coordinates in the string. And in this problem, we are given a length n text t and a shorter length n pattern p. And we want to find the Hamming distances between the pattern p and every shift of the pattern inside the text t. Here is an example. This is a very classic problem in the field of combinatorial pattern matching. And for a long time, the best known algorithm for exactly solving this problem had running time order n root m log m by Abrahamson back in 1807. And this log m factor comes from using FFT. And very recently, there has been some log factor improvements to this result. If we allow Las Vegas randomization, then the best running time completely gets rid of this extra root log n factor. And if we only allow deterministic algorithm, then the best known algorithm still has 1/4 of the log n factor. And in this work, we improve the previous deterministic algorithm to run in n root m log n. So we are only a root log n factor away from the best randomized algorithm. Now let's talk about the techniques of our paper. Similar to many previous works, we follow the hashing-based approach for solving the sparse convolution problem. The idea is that we want to reduce a sparse polynomial to a dense polynomial where the degree is comparable to the original sparsity. More specifically, we pick a hash function from integers to a small set of integers, and when we are hashing a polynomial, we replace the exponent I of each term by the hash value of I. And in order for it to be useful for the convolution problem, we want the hash function to respect addition, that is, h of I plus h of j should be equal to h of I plus j. A very classic example is the mod prime hash, which hashes from integers to the mod p cyclic group. And in this way, hashing a polynomial is equivalent to taking the residual of the polynomial modulo x to the p minus 1. Here is an example instance of sparse convolution. Suppose we use the mod prime hash and we pick the prime p to be equal to 5. Then we can obtain the hashed version of input polynomials f and g, and the degrees of these two reduced polynomials are smaller than p. Then we can use them to compute the hashed version of their product f times g by a FFT in order p log p time. Then suppose we make an ideal assumption that the terms in f times g are isolated under the mod prime hash h. That is, there are no two different terms that are hashed into the same term. Under this assumption, we know that the original answer f times g before the hashing should also have the corresponding terms with the same coefficient with possibly different exponents. Then, in order to recover the exponents, we can use this derivative trick. We can compute the derivative of f times g modulo x to the p minus 1 by expanding it using the product rule and then similarly using FFT. And then by comparing these two polynomials term by term and taking the ratio of the coefficients, we can recover the exponents. So in this example, it happens to satisfy the assumption that all terms are isolated. But in reality, it's hard to guarantee that because of possible hash collisions. So instead, we use a weaker guarantee, which is to recover a constant fraction of the terms, and then iterate this procedure using the iterative recovery framework, which originally came from sparse recovery literature. Here we maintain a current answer polynomial c, and while c is different from the true answer, we try to recover a constant fraction of the terms in the difference polynomial f times g minus c using mod prime hash. Here we have this minus c, but the mod prime hash can similarly take care of this minus c term. And let capital T denote the exponents of the terms in this difference polynomial. If each iteration recovers constant fraction, then we know the size of T should decrease starting from T geometrically, and the whole framework should terminate in order log T rounds. And now the main task is to implement this red line in the pseudocode. And to do this efficiently, we want to pick a prime that is small so that the FFT can be efficient. But at the same time, we also want the hash to be to have high quality when applied to the set T, so that we can use the hashed version of the answer polynomial to actually recover a constant fraction of the terms. And we want to understand the trade-off between the size of P and the quality of the hash function. And here, a good measure of the quality of the hash function is the number of hash collisions, which is defined as the number of I and j from T, where I is different from j, that are hashed to the same bucket under the hash function h. For example, if the number of hash collisions is smaller than T over 2, then we know that at least T over 2 terms are isolated under this hashing h. Because we're taking a random prime, let's look at the expected number of hash collisions. And by linearity of expectation, we care about the collision probability for each pair I and j. Suppose we pick a random prime p from the interval q over 2 and q, and the probability that hi equals hj is the probability that p divides the difference I minus j. And this is equal to the number of prime factors of I minus j in that interval divided by the number of primes in that interval. Because the product of the prime factors should not exceed I minus j, which is bounded by n, we know that the number of prime factors of I minus j is at most log n over log q. And by the prime number theorem, we know that the number of primes in this interval is at least order q over log q. So the collision probability is order log n over q. If we compare this with the fully random hash function into q buckets, where the collision probability is actually order 1 over q. So we can see that here we are losing a log n factor compared to the fully random hash. And actually, this is the main reason why the previous sparse general convolution algorithm pays an extra log n factor in the running time, because they had to choose q to be slightly larger, which affects the running time of the FFT. And this log n factor is exactly what we want to shave in our work. Let's look at the total expected number of collisions, which is just the sum of the collision probability over all pairs, which is roughly t squared over q times this extra log n factor. Let's call this the naive bound. And if the naive bound is tight, then it will mean that most of the differences I minus j would have the worst case number of prime factors in that interval. And the question is whether this is actually possible. In this work, we use tools from analytic number theory, namely the large sieve inequality, which shows that in general, they will not all have this worst case number of prime factors. The large sieve has been used by mathematicians to prove arithmetic properties about some sets. And here we're doing something similar, which is to analyze the prime factors of I minus j, where I and j comes from the set T. Specifically, we need to use this version of large sieve inequality proved by Walker back in 1772. And notice that this condition n is truly subquadratic in Q is the condition of this theorem. And by a standard calculation, we can translate this theorem into the following corollary about the expected number of collision pairs. The bound becomes t times order t over q plus an additive log n factor. Here, if we choose q to be t over log n, then the bound becomes t squared over q, which matches the fully random hash. And this is the key to our improvements for both the sparse non-negative convolution and the sparse general convolution problems. And here, notice that the number of buckets q is actually log n factor smaller than the number of terms that we want to hash. So here we are no longer isolating the terms, but we are hashing them into buckets with average size log n. So this makes our algorithms more technical, and we need to use a lot of extra tools from computer algebra and also from previous works. Here, let me remark that this extra log n term is conjectured to be improvable to constant. So if this conjecture is true, then our algorithm could be much simplified, but it does not. It will not improve the running time because it will only improve a part of the algorithm that is not a bottleneck. In the following, let me give a high-level sketch of our sparse general convolution algorithm. Here is a statement of the theorem. We use the iterative recovery framework, and let's suppose in the current iteration, the number of terms in fg minus c is t prime. And our goal is to recover a constant fraction of the terms in expectation in order t prime log t prime time in addition to the input size. Let's use the mod prime hash where the prime p is chosen as in the previous slide, t prime divided by log n. And we call a bucket as light if its size is smaller than s, where s is defined as 10 times the average bucket size, which is constant times log n. And by the corollary of the large sieve inequality from the previous slide, we get a bound on the expected number of hash collisions, which in turn tells us that in expectation, there are at least 0.9 t prime terms that are hashed into light buckets. And the next step is to correctly recover all the terms in the light buckets. A priori, we don't know whether a bucket is light or heavy, so we could also produce some erroneous terms that coming from the heavy buckets. But this is fine because there are so few of them, and we can still keep making progress. To recover the light buckets, we do as follows. For every k from 1 to 2s, where s is the bound on the bucket size, we compute the hashed version of this polynomial, which is defined as fg minus c, except that every x is replaced by omega to the power of k times x. Here, omega is some element from a large prime field with large multiplicative order. And the total time for computing these polynomials using FFT is p log p times 2s, which is still order t prime log t prime. And we also additionally pay an extra s factor in front of the input size, but it turns out to be actually fine. Now let's focus on the rth bucket, and let's assume it's a light bucket. And let's denote all the terms of fg minus c in this bucket by this polynomial q of x. Then the result from this FFT computation at the beginning will give us all the values of q evaluated at omega to the power of k for k from 1 to 2s. And then using this information, we can recover the polynomial q of x. This task is called sparse interpolation, and it can be done using a version of Prony's method. Prony's method is a general framework for the sparse interpolation problem, and by instantiating it carefully, we can recover q of x in polynomial in the number of terms time, where the number of terms is s, so the time is actually poly log n, and the total time for recovering all the p buckets is strictly smaller than t prime log t prime, which is not a bottleneck. Finally, let me very briefly mention the key new technical lemma behind our improvement for the deterministic textual pattern Hamming distances problem. Informally, this lemma says that under certain parameter regime, given a set of integers a, we can deterministically and efficiently find the modulus m of not too large size that isolates the element, isolates at least half of the elements in the given integer set a. The proof idea of this lemma is to use large sieve inequality and probabilistic method to construct a very small set of moduli that always contains a good modulus. And then we can simply de-randomize by simply trying every modulus in this small set. Finally, let me mention some open problems. First, can we remove the n smaller than t to the 1.99 requirement in our sparse general convolution algorithm? Second, can our de-randomization idea be useful for solving deterministic sparse non-negative convolution problem faster than the previous t times log n to the 5 running time? Thanks for listening.